So hello everyone, this is lecture 25 for the electricity and magnetism. In the last lecture we were discussing about the boundary conditions and we were discussing this example and we did up to here. So in the B1 parallel divided by B2 parallel can be written as mu1 by mu2. So how can we write this? See, when Kf is 0 means current density is 0, then H1 parallel will be equal to H2 parallel. We have seen this here. Now H1 is nothing but we know the relation B equal to mu H. From there H is nothing but B by mu. So B1 parallel divided by mu1 equal to B2 parallel by mu2 because these two are equal. From here you can find B1 parallel divided by B2 parallel is mu1 by mu2. So this will be equal to mu1 by mu2. So if you need to find the tan theta by tan theta 2 will be given by in the terms of mu, that is mu1 by mu2. So let's see one more example that will clear your more concept. The xy plane is the interface between the two different media. Media 1, that is z greater than 0, is filled with a material whose mu r is 4, and medium 2 is z less than 0 is filled with a material mu r 6. If the interface carries the free surface charge current kf equal to 0 and b1 is given 5x cap plus 8z cap, we need to find the h2 and b2. So see, this xy is your interface and there is z greater than 0 is your mu r equal to 4, and there are two medias above this xy plane and the below this xy plane. So below it is 6 and above it is 4, and current density is given 0 and b is given in the first medium, that is 5x cap 8z cap. We need to find b2 and h2. So see, this is our means if we see the b component, then this will represent the perpendicular component, the 8, and this is in the xy plane x cap, so that will be your parallel component. So we know b1 parallel is 5 x cap and b1 perpendicular is 8 z cap. If there was some y component, then that will also be included in the parallel component. So here we have only these two. Now see, we know b1 perpendicular will always be equal to b2 perpendicular because that will be continuous always. So b2 perpendicular will remain same, that is 8z cap. Now we need to find what will be b2 parallel, because if we know the b2 parallel, then just parallel and the perpendicular component will give us the complete b2. So let's see, if kf is 0, then h2 parallel will be equal to h1 parallel, and this relation we already seen that will imply that b2 parallel divided by mu2 equal to b1 parallel by mu1. From here you will find the b2 parallel, that will be equal to b1 parallel, we already know 5 divided by multiply 6 mu naught divided by 4 mu naught. So b2 will be 7.5 x cap, this b2 parallel. Now we have b2 parallel and we have the b2 perpendicular. So b2 can be written as in the sum of these two. So this is b2 and we know h2 is nothing but b2 by mu2. So just put b2 here and mu2 we already know, that is mu naught and mu r in the 2 is 6. So it will be 6 and this, so it will give you h2. Now see, that's how you can find the h2 and b2. Let's say if now kf is not 0, kf is given something, means charge, there is some current density, that is 1 upon mu naught y cap. Then how our h1, h2 and b2 will change, means how can we find then h2 and b2? So see, perpendicular component still remains same, but we know that this relation h1 parallel is not equal to h2 parallel. If kf is something, then this will be equal to kf cross n cap, and we know h1 parallel is b1 parallel divided by mu naught mu. So that will be b1 parallel is 5 divided by 4 is mu r in the first medium, and the mu naught x cap minus this is, let's assume we don't know the b2. So what we do, we just assume b2 as some bx x cap and by y cap, and divide by this is mu r mu naught, this is in the first medium, sorry in the second medium, this is for the first medium, and for the second medium just we assume that b2 is this, and divide by mu and mu naught. So this will be 6 mu naught, because for the second medium it is 6. So I hope it is clear to you. Let me repeat again. This is our h1 parallel is b1 parallel divided by mu. So b1 parallel is 5 divided by 4 is mu r for the first medium, mu naught x cap. Now see, this is the parallel component, that's why I have written here it is x cap. Now h2 parallel is b2 parallel divided by, and it will be 6 is mu r for the second medium and mu naught. So I assume that in the xy plane the parallel component will be in the x and y terms. So we are assuming here only parallel component, so this will be divided by 6 mu naught equal to kf is given as 1 upon mu naught y cap multiply cross product with the n cap is in the direction of z cap, because this is the interface xy, so perpendicular component will be in the z cap direction. Now see, what we do, we'll just take this y cross z will give you x cap. So we'll take the x cap common here, and we can just compare them. 5 by 4 mu naught minus bx by 6 mu naught will be equal to 1 upon mu naught, and bx by 6 mu naught will give you 0 because there is nothing for the y cap. So just after comparing right and left side, we'll get this term equal to 1 upon mu naught, and by will be equal to 0. From here we can find the bx. So bx will be 1.5. So we have bx and we have by, so we have the b parallel component, b2 parallel component. that will be 1.5 x cap, and we know the perpendicular component will remain same, so complete B2 will be given by this, and S2 will be B2 by mu2. So we have S2, we have B2. So if it is not 0, means current density is not 0, then that's how you find the B2 and S2. So here our magnetostatics is completed. Now let's start today the electrodynamics. So what we will study in the electrodynamics, we will study that how the moving closed conductor or the closed loop, which means which is moving in the uniform magnetic field or the non-uniform magnetic field, then the EMF or the electromotive potential, means the potential difference will be induced in that conductor or the loop, and that is what we study in the electrodynamics, the Faraday law and all. So first let's see, if there is some circuit and there is some potential difference, then there will be some current. But what if here the current is due to the electric field in this? So if there is not this is not available, the battery, and this complete thing is moving in a magnetic field, then there will be charges in this wire which are moving in the direction in the magnetic field. So they will feel some force, and that force will move those charges, and again we will get some potential difference that we call the electromotive potential, that is EMF, and that will give us the current. Now when there is battery also and it is complete is moving in the magnetic field, then we have the force due to both of the things, the magnetic field and the electric field. But the magnetic field force will be very small because the speed will be very small. So let's see some things. Let sigma be the conductivity of the material for this material, this wire, and current density is given by J sigma F. We know from the Ohm's law, J is given by sigma E when there is only electric, means we have some circuit. So here this F represents the force per unit charge. So if there is only electric field, then this force per unit charge is nothing but E. So sigma E, J equal to sigma E, you know that relation. So but here it is also moving in the magnetic field, so it is given by complete force per unit charge is E plus V cross B. So this is total force is Q E plus V cross B. So divided by per unit charge will give you E plus V cross B. Now see, this is very negligible, means speed is very negligible and give us very low J. So that's why we will consider J equal to sigma E for the ideal case. In the when we consider some circuit, we assume only J equal to sigma E. So V cross B is neglected. So J equal to sigma E, this is nothing but Ohm's law. How can we get the Ohm's law from this relation? See, this J is nothing but current per unit area, and E is given by V by L. Here V is the potential in this circuit. So V by L, and this sigma is nothing but conductivity. From here you can see that V equal to L by sigma I. Now this is nothing but resistance, V equal to IR, and resistance is L by rho sigma A. Now 1 upon sigma is given by rho, and R equal to rho L by A. We know this relation, this is resistance. So that's how we can just derive the Ohm's law from this relation. So this relation is nothing but Ohm's law. So the actual relation is this, but we use this relation in the circuits, electricity. But in the actual cases, we consider this thing, J equal to sigma F. So let's see the case. Now there is no battery available, and there is this current loop, means not current loop, this is some conducting loop, and this is having some resistance R, and it is completely moving in V in this direction with the speed V, and there is the magnetic field available. Now this is moving in this direction. So see, this charges in this wire will also moving in this direction, and V cross B will give you force in this direction if this is the positive charge. Then the charge will feel the force in this direction and move like this. So the charge moving will give you the current, and see here the charge can't move because this can't go outside the wire. Here also it can't move, but see, feel the force same side. So only this wire will give you the EMF, that is the electromotive force or the EMF potential. So what will the kind, means this will be look like this. So we can just remove this with a battery like plus minus, and this will be your EMF. So the moving V velocity will give you your EMF, and what is the value of this EMF will be given by the force per unit charge felt by this charge multiply the distance traveled dl. So integrating for the complete length, this length, and force per unit charge will be F magnetic only because there is no electric field. So F magnetic dot dl will give you the complete EMF induced due to this motion. So see, here the force magnetic per unit charge is nothing but V cross B only, because total force is Q V cross B, and per unit charge will give you V cross B only. So just write here V cross B. Now V and B are perpendicular, so it will give you VB only, and dl. Now integrating for the complete length, let's say this length is h, so it will give you VBH. So this is your EMF induced in this wire. Now we can just also find this in terms of the flux. So let's see what will the flux. Flux will be magnetic field passing through this area. So it will be given by this B dot dA, and d is nothing but, if this distance is x and this is h, so only this part is having the flux, so it will be hx the area, so bhx, this will be the flux. Let's take the time derivative, it will give you d phi by dt, and this is bs dx by dt. Now see, this dx by dt will be negative because it is moving outside, so this x is reducing, that's why we will have dx by dt as minus v. This will be equal to minus bhv, and bhv we already find is given by the potential, so EMF is E, so it will be minus E, d phi by dt will be minus E. From here, electromotive potential is nothing but minus d phi by dt. So this relation is very important. The potential will be given by minus d phi by dt. And this is also, this negative sign represents the Lenz's law. And what is the Lenz's law? Lenz's law says that the EMF will be induced in that way. It means it will oppose the flux change. It will oppose the flux change. Means if the flux is increasing, then this EMF will be induced like it will decrease the flux. And if the flux is decreasing, then EMF will be induced like it will increase the flux. And that's how we can reduce the direction of induced current also. So let's see how it will be. See, if this is moving outward, then this flux is reducing, so it should be increased. So current will be in this way, so that magnetic will be in that direction going inward, so that magnetic field will increase and flux will increase. But if it is going this side, then flux will increase, so it should decrease, so current will be in this direction, so that the net magnetic field will be reduced or the flux will be reduced. So that's how the Lenz's law or this negative sign represent that how the EMF will be induced, so that it can oppose the change in the change in the flux. So the EMF will be induced in that way that it will oppose the change in the magnetic flux. Okay, the time change in the magnetic flux. So that's how you just see what is Lenz's law, and it is valid in all conditions. Whether you have the symmetrical structure or the unsymmetrical structure, it will be always be valid. So let's see some examples based on these things. So we have a conducting disc, and this is rotating like this with the angular velocity omega, and this is connected with a wire, and this is just touching this disc, and this is rotating, and here also it is touching this. Now see, when this is rotating like this, then every positive charge is moving in this direction, so V is in this direction tangential, and now B is in the perpendicular direction, so V cross B will give you the force in the outward direction. Means every charge will feel the force in the outward direction, going outward. So that charge will flow like this. After this, it will go like this and this way. So current will be in this way. So that's how your current will be induced. So now let's see what will the means EMF will be induced here. So that is, first we need to find the force per unit charge, means F magnetic on this charge. So that will be given by V cross B, and the EMF will be given by F magnetic dot dl, and this is V cross B. So VB are perpendicular to each other, so it will be VB only and dr. Now see, this charge is moving from this point to this point, so this we need to integrate from 0 to r, and here radius is given as a, so it will be integrated from 0 to a. Now V is nothing but r omega. At any point the tangential velocity is given by r omega. This is the speed, so V will be r omega b dr. Now this will be r dr will give you r square by 2, and integrating 0 to a will give you a square by 2. So your EMF will be omega b a square divided by 2. Now from here you can find current also. V is equal to IR. Current is nothing but V by R. So E by R will give you this omega b a square divided by 2R. Resistance is R. So this will be your current induced here. Now see, if you have some rod and it is moving with V velocity in this direction, then it will, the charge, if we have electron here, then that will feel the force in this direction because this is a negative charge. So here the negative concentration will increase, and here the positive concentration will increase. So see, when this concentration is starting to increase, then there will be a electric field created in this direction. So electron will feel force in this direction also. So at one point it will come that net force will be 0 on this electron. So that point will be when electric force will be equal to magnetic force, that is E equal to EVB, and this E is nothing but V by L. This V is potential, V divided by this length will give you the electric field. So EV by L equal to EVB, and this V is velocity. So here this V potential is given by VBL, and this is just the same as we have find it here from this formula. This was the same actual, means here the length was H. If it is L, then again it is VBL. So we are getting the same potential by both ways. So see, so now we can generalize this thing, that we are getting the same expression. So we can write that any rod will feel the same force if it is at the angle theta with the B, and it is moving some V direction, and this angle is alpha, and this L is length. and this is in this direction. So the net EMF can be given by this expression V cross BL. So this is the general expression you can find on any conducting rod. The net EMF will be in this way, that is V cross B dot L. Now see, you must remember this expression for any this. Now this, if theta is 90 degree, then this will be again VB and dot L. So this will give you the same expression. But see, this L, if any two will be parallel here, then this net EMF will be 0. So they can't be parallel. So if any two vector BLB are parallel, then E is 0, because this is perpendicular, and if that perpendicular is this, it will give you 0. So we can take an example also. See, this rod is in this direction and B is in this direction, and it is moving like this. So see, B and L are parallel, so EMF will be 0. And see, any two are parallel, then it will be 0. Means if it is in this direction, L is in this direction, V in this direction, so it will again 0. So it must be in some other way, means they can't be parallel. So you must remember this result. This is a generalized case. For any case you can apply. So that's all for today. Thank you everyone.